On April 6, 2026, 4 astronauts disappeared behind the far side of the Moon. For 40 minutes, no signal reached Earth. This was expected. It happens on every lunar mission. The Moon blocks the line of sight and the crew goes dark. But what the Artemis II crew saw during those 40 minutes was, what they reported when the signal came back was something no one at Mission Control had expected to see. So, let's go behind the Moon. To understand why this moment mattered so much, you need to understand how far away these 4 people actually were. At 7:02 p.m., just minutes after Orion emerged from the far side and the Deep Space Network reacquired its signal, NASA confirmed that the crew had reached a distance of 252,756 miles from Earth. That is the farthest any human being has ever traveled from this planet. The previous record was set by the Apollo 13 crew in 1970 at 248,655 miles. Artemis II broke that record by 4,111 miles. Now, numbers like that are hard to feel. So think of it this way. Light itself, the fastest thing in the universe, would take nearly a second and a half to travel from Earth to the Orion spacecraft at that distance. The spacecraft was screaming past the Moon at about 60,863 miles per hour relative to Earth. But relative to the Moon itself, it was moving at only about 3,139 miles per hour, slow enough for the crew to study the terrain below them in detail. That dual speed is worth pausing on. The spacecraft is not slowing down. It is simply that the Moon and Orion are moving in roughly the same direction, at roughly the same rate. It is the difference between watching a car pass you on the highway at full speed and watching that same car from another car driving alongside it. From one frame of reference, it is a blur. From the other, you can read the license plate. And the crew needed to read the license plate, because what they were doing during that flyby was not just sightseeing, it was science. Carefully planned, methodically structured science that had been in preparation for months. And the Moon gave them far more than they expected. Long before Orion left Earth, a team of lunar scientists had been working with the crew to prepare an observation plan. The mission's lunar observation period was designed to last approximately 7 hours. That is the window of time during which the spacecraft would be close enough to the Moon within about 4,070 miles at closest approach to make impactful scientific observations. During this window, the spacecraft was oriented so that its windows pointed directly at the lunar surface. At 1:30 p.m., on the day of the flyby, NASA's lunar science officer briefed the crew on their objectives. The science team had sent up a final list of 30 lunar surface targets on April 5th. These were not random features. Each one had been selected for its scientific significance. Among the most important was the Aitken Basin. This is a nearly 600-mile-wide impact crater that straddles the boundary between the Moon's near side and its far side. It is estimated to be 3.8 billion years old. It formed when a large object struck the lunar surface with enough force to leave behind dramatic topography, concentric rings radiating outward from the point of impact that are still clearly visible today. Orion is considered the textbook multi-ring impact basin. It is the baseline that scientists use to compare other impact craters on rocky worlds from Mercury all the way out to Pluto. And Artemis II marked the first time that human beings had seen the entire basin with their own eyes. The crew would continue to observe Orion from multiple angles as they approached the Moon and throughout the flyby, building a visual record that no camera could fully replicate. Another key target was Hertzsprung Basin, a nearly 400-mile-wide crater on the Moon's far side, northwest of Orion. Hertzsprung is older. Its features have been degraded by subsequent impacts over billions of years, which makes it a valuable contrast to Orion. By comparing the topography of these two craters, one relatively well-preserved, the other deeply worn, scientists hope to gain insight into how lunar features evolve over geologic timescales. The crew was also tasked with observing Rhina Gamma, a bright, mysterious swirl on the near side whose origin scientists are still trying to understand, and Glushko, a bright 7-mile-wide crater known for the white streaks that radiate out from it for up to 500 miles. As Orion approached the moon on the near side, people in parts of the eastern hemisphere could actually view some of the same features the astronauts were observing. For a brief stretch of time, both the crew in space and observers on the ground were looking at the same craters, the same terrain, the same ancient scars. But then Orion crossed over to the far side, and the view changed completely. The far side of the moon is not the dark side. That is a common misconception. It receives just as much sunlight as the near side, but it is the side that never faces Earth, which means it had never been seen by human eyes until the Apollo 8 crew flew around the moon in 1968, and it looks nothing like the near side. The near side has large, dark, flat plains, the ancient lava flows we call Maria. The far side has almost none of those. Instead, it is a chaotic, heavily cratered landscape. It looks older, rougher, more battered by time. And buried within that battered terrain is one of the most intriguing features in the entire solar system, the South Pole Aitken Basin. Measured from outer rim to outer rim, this crater is about 1,600 miles in diameter and more than 8 miles deep. It is the largest known impact crater in the solar system. Its existence had been suspected since 1962 based on data from the Lunar 3 and Zond 3 orbiters, but it was not confirmed until the mid-1960s by the Lunar Orbiter program. And beneath it, something strange is hiding. In 2019, a study published in the journal Geophysical Research Letters revealed that researchers had detected a large, anomalous mass buried deep beneath the basin floor. Using data from NASA's Grail mission, which measured very small changes in gravity around the moon, combined with topography data from the Lunar Reconnaissance Orbiter, scientists found an unexpectedly large concentration of dense material hundreds of miles beneath the surface. The mass is enormous. To put it simply, imagine taking a pile of metal 5 times larger than the big island of Hawaii and burying it underground. That is roughly the scale of what was detected. So what is it? The leading hypothesis is that it is the iron-nickel core of the asteroid that created the South Pole Aitken Basin roughly 4 billion years ago. Computer simulations of large asteroid impacts suggest that, under the right conditions, the metallic core of the impacting body could become lodged in the upper mantle of the moon, the layer between the crust and the core, and remain suspended there rather than sinking deeper. The math supports this. A sufficiently dispersed asteroid core could remain in place until the present day. There is one other theory. The mass might be a concentration of dense oxides associated with the last stage of lunar magma ocean solidification. Billions of years ago, the moon may have been covered not by water, but by an ocean of molten rock. As that magma cooled and solidified, dense oxides could have been deposited in this region, forming the mass we detect today. Either way, the South Pole Aitken Basin remains one of the best natural laboratories for studying catastrophic impacts in the early solar system. And in January 2019, China's Chang'e 4 spacecraft became the first craft ever to land on the far side of the moon, touching down within this very basin, inside the smaller von Karman crater. This is the terrain the Artemis II crew was flying over. This is what they were looking at when the radios went dead. At 6:41 p.m., just 3 minutes before the communications blackout began, the crew witnessed something extraordinary, an Earthset. As Orion traveled behind the moon, the Earth, that small, bright blue point that had been visible through the spacecraft's windows for days, dropped below the lunar horizon and disappeared. It did not fade. It did not dim. It simply sank behind the edge of the moon and was gone. For about 40 minutes, the crew could not see their home planet. Every person they had ever known, every place they had ever been, every sound and color and breath of wind that had ever mattered to them was hidden behind a wall of ancient grey rock. It is a perspective that fewer than 30 human beings have ever experienced, and it does something to you. Every astronaut who has described it uses slightly different words, but the core of the experience is the same. The Earth becomes small, and the universe becomes very, very large. Pilot Victor Glover, just before the signal was lost, spoke to the ground one final time. He said that even as they prepared to lose radio contact, they could still feel the love from Earth. He told everyone listening on Earth and around Earth that the crew loved them from the moon and that they would see them on the other side. Then the signal cut and the crew was alone. Now, more than 50 years ago, the Apollo astronauts experienced this same isolation, perhaps none more profoundly than Apollo 11's Michael Collins. In 1969, while Neil Armstrong and Buzz Aldrin made history on the lunar surface, Collins was alone in the command module, orbiting above them. As his craft passed behind the far side, contact with the pair on the surface and with mission control vanished for 48 minutes. He described the experience in his 1974 memoir, saying he felt truly alone and isolated from any known life. But he also said he did not feel fear or loneliness. In later interviews, he described the peace and tranquility brought by the radio silence, saying it offered a break from the constant requests from mission control. The Artemis II crew had a different job during their blackout. They were not resting, they were observing. Every minute of that silence was dedicated to lunar science, photographing the surface, studying the geology, and simply looking out the window at a landscape that no human eyes had studied at this distance in more than half a century. When the signal came back, everything changed. At 7:24 p.m., the crew witnessed an Earthrise the moment the Earth reappeared above the opposite edge of the lunar horizon, and moments later, the Deep Space Network reacquired Orion's signal. Communications were restored, but it was what the crew reported next that caught everyone off guard. As Orion entered the shadow of the moon near the end of its closest approach, the sun dipped behind the lunar disk, creating a solar eclipse that lasted almost an hour. During this phase, the crew could see the solar corona, the sun's outermost atmosphere, glowing around the lunar edge. This was not like watching a solar eclipse from Earth, where the atmosphere scatters light and the sky never goes fully dark. This was a solar eclipse in the vacuum of space, seen from behind the moon, at a distance no living human had ever occupied. The corona would have appeared as a ring of ethereal, pearly white light surrounding the dark silhouette of the moon, sharp, clean, and impossibly bright against the blackness. The crew was tasked with studying the corona and watching for something else, flashes of light from meteoroids striking the lunar surface. The mission science team had briefed the crew on this possibility. Impact flashes are caused by micrometeors hitting the moon, and observing them could offer insight into potential hazards on the lunar surface. It was on the checklist, but nobody expected what actually happened. The crew reported witnessing no fewer than 5 separate micrometeor impacts on the lunar far side. 5 distinct flashes of light, tiny, ancient rocks slamming into the moon at incredible speeds, each one releasing a brief burst of energy visible to the naked eye from Orion's windows. Now, think about what that means. The moon has no atmosphere. There is nothing to slow these objects down, nothing to burn them up before they reach the surface. A micrometeor approaching Earth would hit the atmosphere and likely disintegrate into a harmless streak of light, a shooting star. But on the moon, every single one of them hits the ground, at full speed. And when they do, the kinetic energy is converted instantly into a flash of light and heat. The Artemis II crew, during the darkened phase of the eclipse, could see those flashes with their unaided eyes. This was the first time any human had witnessed micrometeor impacts on the moon from lunar space, and it happened 5 times in a single observation window. Back in the science evaluation room at Johnson Space Center, where lunar scientists were supporting the observations in real time, the reaction was immediate. There were audible screams of delight, according to Kelsey Young, Artemis II's lunar science lead. The scientists were not expecting this, not at this scale, and the impacts were not the only surprise. Throughout the flyby, a lively stream of science observations from the crew had been pouring in. The astronauts reported color nuances on the lunar surface, shades of browns and blues that could be picked out with human eyes, and that could help reveal the mineral composition of surface features and their age. As each report came in, the science team in Mission Control updated the observation plan, sent follow-up questions, and transmitted new guidance to the crew. This was the part that no robotic mission could replicate. Human eyes, human judgment, human intuition processing visual information in real time, noticing details that cameras might miss, responding to what they saw with the kind of adaptive curiosity that only a person can bring. As Kelsey Young put it, this was absolutely everything they hoped for by integrating science into flight operations. Science enables exploration, and exploration enables science. Shortly after 2 p.m., before the blackout, the crew had done something deeply human in the midst of all that science. They named 2 craters. As Orion passed over the heavily pockmarked lunar surface, the astronauts described 2 small, unnamed craters that they could see with their naked eyes. Calling down to Earth, they suggested provisional names for them. The first, located just northwest of the Orion Basin, they proposed to call Integrity after their spacecraft and this historic mission. The second, just northeast of the Integrity crater, sitting on the boundary between the Moon's near and far sides, and sometimes visible from Earth, the crew suggested be named Carol. This was in honor of Reed Wiseman's late wife, Carol Taylor Wiseman, who passed away on May 17, 2020. After the mission, these crater name proposals would be formally submitted to the International Astronomical Union, the organization that governs the naming of celestial bodies and their surface features. It is a small moment in the context of a 10-day spaceflight, but it is also the kind of moment that makes space exploration more than a technical achievement. The Moon is 4.5 billion years old. Those craters have been sitting there, unnamed and unseen by human eyes, for eons, and now, 2 of them carry the name of a spacecraft built to go farther than any crewed vehicle before it, and the name of a woman who never got to see it fly. That is what happens when you send people to the Moon instead of machines. And there was one more light-hearted milestone that day. NASA Flight Director Brandon Lloyd, Capsule Communicator Amy Dill, and Command and Handling Data Officer Brandon Borter sent an email to the crew shortly after 2 p.m. It is now assumed to be the longest person-to-person message ever transmitted in human history, not because of its length on the page, but because of the distance it had to travel to reach its recipients. While the crew was looking out the windows, something else was looking inward. Mounted inside the Orion spacecraft were 6 time-pix chips, advanced sensors for particle and radiation detection that had been developed at CERN, the European Organization for Nuclear Research. These chips were part of the MEDIPIX 2 collaboration, an international project involving the National Institute for Nuclear Physics and research groups from several Italian universities. During the approximately 10 days of the mission, these devices monitored, in real time, the characteristics and level of radiation inside the spacecraft. This was not optional data. This was a crucial measurement. Here is why. Inside the protection of Earth's geomagnetic field, the invisible magnetic bubble that surrounds our planet, radiation levels are manageable. Astronauts on the International Space Station, orbiting at low Earth altitude, are shielded from the worst of it. But once you leave that protection, as the Artemis II crew did, you are exposed to significantly higher levels of radiation. Galactic cosmic rays, high-energy particles that originate far outside our solar system, constantly bombard anything that is not shielded by a planet's magnetic field. When those cosmic rays strike the spacecraft, they do not just bounce off. They generate secondary particles, charged fragments, neutrons, pions, muons, electrons, and positrons that scatter through the cabin. Understanding the nature and intensity of that radiation is essential for protecting both the crew and the onboard electronics. The Timepics chips are part of the Hera system developed by NASA, and they are remarkably good at this job. The technology derives from hybrid pixel detectors used in experiments at the Large Hadron Collider, the most powerful particle accelerator in the world. These sensors can distinguish different types of radiation by analyzing the tracks left by particles in much the same way that the enormous detectors in experiments like ATLAS, CMS, and ALICE identify subatomic particles at CERN. So while the crew was gazing at craters and naming features on the moon, particle physics detectors, born from the world's most advanced accelerator experiments, were quietly cataloging every stray cosmic ray that made it through the walls of their spacecraft. That is the kind of detail that does not make the evening news. But it might be the detail that determines whether humans can safely travel to Mars. There is a strange footnote to the history of humans flying behind the moon that deserves mentioning here, not because it is relevant to Artemis II, but because it reveals something about how silence affects people in space. During the Apollo 10 mission in May of 1969, the dress rehearsal for the first lunar landing astronauts Gene Cernan, John Young, and Tom Stafford flew around the far side of the moon and lost contact with Earth, just as every crew before and after them has done. But during that silence, something odd happened. The crew began hearing a strange whistling sound. Cernan described it as outer space-type music. The three men agreed it was really weird, and Young said they were going to have to find out about it, because nobody would believe them. It turned out to be nothing more than interference between the VHF radios on the command module and the lunar module, two vehicles flying in close proximity, their radio systems creating a harmonic feedback loop. Apollo 11 astronaut Michael Collins later wrote that NASA technicians had warned him about the whistling before his own mission. He said that if he had not been warned, it would have scared him. The explanation was straightforward. But what is interesting is that the crew did not discuss the sounds publicly for years. The likely reason, as some have suggested, is that the astronauts did not want to project anything but absolute confidence. Any indication that something had rattled them during a flight might have gotten them grounded. The Artemis II crew did not report any mysterious sounds, but they did experience the same profound isolation, the same radio silence, the same darkness, the same awareness that every known human being was on the other side of 250,000 miles of empty space. And unlike Collins, who was alone in his module while his crewmates walked on the surface below, the Artemis II astronauts had each other, 4 people, together in the silence, watching the far side of the moon roll past beneath them. Getting to the moon is only half the problem. Coming home is the other half. When Orion re-entered Earth's atmosphere at the end of the mission, it was traveling at approximately 25,000 miles per hour. At that speed, the friction between the spacecraft and the atmosphere generates temperatures that can destroy almost any material. The only thing standing between the crew and that heat was the Orion capsule's heat shield, and the heat shield had a history. During the uncrewed Artemis I mission in late 2022, the Orion capsule's heat shield experienced unexpected char loss. Instead of wearing away gradually as designed, the protective material chipped off in larger than expected pieces, leaving the shield streaked with burns and missing sections. This was the Artemis I mission, the one that had been sent to test the vehicle in preparation for the first crewed flight. Its trajectory had taken Orion on an approximately 2 5-day journey, entering a distant retrograde orbit around the moon before returning to Earth. The vehicle performed well in almost every respect, but the heat shield was the exception. This became the primary safety concern heading into Artemis II. If the shield failed to hold while hitting the atmosphere at those speeds, the result could have been fatal. NASA took this seriously. Before Artemis II flew, engineers modified the re-entry angle of the capsule to reduce the duration of peak thermal stress. They also conducted extensive ground testing at arc jet facilities to predict how the material would behave under the adjusted conditions. The approach was methodical: change the angle, test the prediction on the ground, then fly the mission and see if reality matched. And it worked. After splashdown in the Pacific Ocean off the coast of California, US Navy divers captured photos of the heat shield within moments of the crew's arrival. Early data showed that the char loss behavior observed on Artemis I had been significantly reduced, both in terms of quantity and size. The performance was consistent with the ground testing that had been performed after the first mission. The technical adjustments had performed exactly as predicted. Looking at the photos, the heat shield appeared remarkably intact. One observer noted it almost looked like you could fly it again. The crew module would be delivered to Kennedy Space Center for detailed inspections, post-flight data retrieval, and removal of reusable components. Later, over the summer, the heat shield itself would go to Marshall Space Flight Center in Alabama for sample extraction and internal X-ray scanning. But the early verdict was clear. The heat shield held, the modifications worked, and the crew came home safely. Here is something most people do not realize. There are already scientific instruments on the moon that were placed there decades ago, and some of them are still working. Starting in 1969, during the Apollo 11, Apollo 14, and Apollo 15 missions, along with the Soviet Lunokhod 1 and Lunokhod 2 rovers, special devices called laser retroreflectors were installed on the lunar surface. These instruments are beautifully simple. They consist of arrays of corner cube retroreflectors, precisely shaped mirrors that reflect light exactly back in the direction it came from. This allows scientists on Earth to perform what is called lunar laser ranging. The method works by sending short laser pulses from ground stations toward the moon, bouncing them off the retroreflectors, and measuring the time it takes for the light to make the round trip. From that measurement, you can calculate the Earth-Moon distance with extraordinary precision. Over the past 55 years, these measurements have produced remarkable scientific results. They have enabled very accurate tests of general relativity. They have revealed information about the internal structure of the moon. They have provided precise data on the moon's motion and on the position of both the reflectors on the lunar surface and the laser stations on Earth. But the old reflectors have a problem. The precision of Earth-based laser stations has improved dramatically over the decades, but the reflectors themselves have not changed. Their accuracy is now limited by something called lunar librations, apparent oscillations of the moon caused by the shape and inclination of its orbit. These librations introduce measurement uncertainties that are larger than what modern laser technology could achieve if the reflectors were better. So a new generation of reflectors is being built. The Moonlight project, developed at the INFN National Laboratories of Frascati in Italy, has created a single large corner cube retroreflector, 100 mm, that is far more precise than the old configurations and designed not to be affected by librations. The instrument requires very accurate pointing toward Earth. Its field of view is limited to a narrow cone, while lunar librations can shift the moon's apparent orientation by a significant amount. To solve this, the team developed a dedicated pointing system called Moonlight Pointing Actuator, designed to orient the reflector with great precision through two perpendicular rotational movements, even in the extreme conditions of vacuum and temperature on the lunar surface. This system was completed, qualified, and accepted by ESA, NASA, and the company Intuitive Machines in 2023. In 2025, the first of these next-generation reflectors was successfully installed on the moon through a NASA mission. A second reflector is planned for launch by the end of 2026 through a joint NASA-ESA mission within the Commercial Lunar Payload Services program. The destination for that second reflector is Rhina Gamma, the same mysterious swirl that was on the Artemis II crew's observation list, the same feature they studied with their own eyes during the flyby. And the technology does not stop at the moon. In parallel with moonlight, miniaturized laser retroreflector technology has already been sent to Mars. In 2018, a micro-laser reflector called LARI was placed on board NASA's InSight lander. Another, called LARA, was deployed on NASA's Perseverance rover, which has been searching for signs of life on Mars since 2021. The same miniaturized technology was also applied to China's Chang'e 6 mission, which successfully landed on the far side of the Moon. From the Large Hadron Collider, to the far side of the Moon, to the surface of Mars, everything is connected. And then there are the ideas that have not been built yet, the ones that sound almost too ambitious to be real. One of them is LGWA, the Lunar Gravitational Wave Antenna. This is a project that aims to detect gravitational waves directly from the Moon, not from orbit, not from a space telescope, from the Moon itself, using the lunar surface as the detector. The idea dates back to the 1970s, to the work of the American physicist Joseph Weber, who contributed to the development of the lunar surface gravimeter installed during the Apollo 17 mission. That experiment did not succeed due to a technical problem, but the intuition behind it that you could use a world-sized object as an antenna for gravitational waves has never gone away. In 2023, ESA selected LGWA within its reserve pool of science activities for the Moon, giving it the highest evaluation among all proposals submitted. The Italian Space Agency subsequently funded the preparatory studies, covering the first 2 years of development with the possibility of extending activities beyond 2027. The project is being developed by a consortium led by the Gran Sasso Science Institute, involving the University of Camerino, the National Institute for Astrophysics, the National Institute of Geophysics and Volcanology, and the National Institute for Nuclear Physics. Activities are currently focused on the technological development of the lunar payload, along with characterization of the lunar soil through modeling of seismic wave propagation. The scientific objective is extraordinary. LGWA aims to observe signals from compact binary systems, from white dwarfs in our galaxy to massive black holes at cosmological distances. It would also study the internal structure of the Moon and the mechanisms behind its seismic activity. There is also LEM-X, the Lunar Electromagnetic Monitor in X-rays, a project to install soft X-ray sensors on the lunar surface for continuous sky monitoring. The instrument would be built in a dome-shaped modular structure, with each module pointed in a different direction, allowing it to observe half the sky at once. Over time, as the Moon rotates, the entire celestial sphere could be surveyed. The technology is rooted in detectors originally designed for the ALICE experiment at CERN's Large Hadron Collider. The Moon, it turns out, is not just a destination, it is becoming an observatory, a platform, a place where the instruments we build to study the smallest particles in the universe are being repurposed to study the largest structures in the cosmos. And the Artemis II flyby was a step toward making all of that real. More than 50 years after the Apollo missions, the Moon has once again become the main objective of the major space powers. China aims to land its astronauts on the lunar surface by 2030. NASA plans a new crewed moon landing by 2028. It is a competition that closely recalls the early days of the space age, when the Soviet Union and the United States faced each other in a race that defined a generation. But this time, the race is different. It is not just two nations. It is a global effort: American, European, Canadian, Chinese, Indian, Italian, Japanese, converging on the same ancient target for different reasons, but with the same underlying impulse. The impulse to know, the impulse to see, the impulse to go. When the signal came back at 7:24 p.m. and the crew saw Earth rising above the lunar horizon, something shifted. The blackout had lasted roughly 40 minutes. In that time, the crew had seen the far side up close. They had witnessed micrometeor impacts that no human had ever observed before. They had studied craters and color gradients and geological features that would take months to fully analyze. They had floated through the deepest silence a human being can experience, cut off from every other person alive, farther from home than anyone had ever been. And then they came back. Jeremy Hansen, the Canadian Space Agency astronaut, had spoken before the blackout about the record the crew was about to set. He acknowledged the extraordinary efforts of the Apollo missions that came before them. He said they chose that moment to challenge this generation and the next to make sure the distance record they were setting would not be long-lived. That is the thing about records in spaceflight. They are not meant to stand forever. They are meant to be broken. Back on Earth, at the Goonhilly Earth Station in Cornwall, England, a huge antenna had been tracking Orion's signal throughout the mission, carefully pinpointing the spacecraft's position and feeding that information back to NASA. It was the first time Goonhilly had tracked a spacecraft carrying humans. When the blackout began, the team there held their breath. When the signal reappeared, they knew the crew was safe. But the chief technology officer at Goonhilly pointed out something important. These communications dropouts, he said, would need to become a thing of the past. For a sustainable presence on the moon, the kind of presence that NASA and other space agencies are now actively planning, you need continuous coverage, 24 hours a day, even on the far side. Especially on the far side, because the far side will need to be explored as well. Programs like the European Space Agency's Moonlight Initiative are already planning to launch a network of satellites around the moon to provide exactly that continuous, reliable communication coverage for future missions. When that network is in place, no crew will ever lose contact with Earth during a lunar flyby again. The silence will become a relic of a different era. And that era, as of April 2026, may already be ending. The silence the Artemis II crew experienced may be one of the last of its kind. For all that the Artemis II mission accomplished, for all the data collected and records broken and craters named, the moon remains deeply mysterious. There is still an unexplained mass the size of Hawaii buried beneath the far side's largest crater. There are still swirling patterns on the surface whose origins no one fully understands. There are ancient impact basins that hold clues to the violent early history of the solar system, and we have only begun to read them. The 5 micrometeor impacts the crew observed raise their own questions. How frequent are these events? What do they tell us about the lunar environment that future astronauts will need to survive in? What hazards remain invisible from orbit that only human eyes on the surface could detect? And somewhere inside the Orion spacecraft, 6 tiny chips designed to track subatomic particles at the Large Hadron Collider spent 10 days quietly measuring the cosmic radiation that any future crew headed to Mars or beyond will need to withstand. The moon is close. It is only about 240,000 miles away on a good day. We have been staring at it for all of human history. We have walked on it, driven on it, left mirrors and flags and footprints on its surface. But we do not understand it. Not yet. Not fully. China's Chang'e 4 landed on the far side in 2019 and studied material that may have come from deep within the moon's mantle. Next-generation laser reflectors are being placed on the surface. Plans are being drawn up to install gravitational wave detectors and X-ray observatories on the lunar ground. The moon is being transformed from a destination into an instrument, a platform for answering questions we have not even thought to ask yet. And that is what makes it worth going back. The Artemis II crew spent 40 minutes in silence behind the moon. They emerged with data, with photographs, with observations that scientists are still processing. They came back with stories about flashes of light on an ancient surface, about craters named after love and integrity, about the corona of the sun glowing behind the dark edge of a world no one on Earth could see. Every answer brought another question, and that is exactly how science moves forward. For now, the moon waits, and we are just getting started.